Good afternoon, everyone. Today, my colleagues Steven Hurtado and Andres Hernandez are going to talk about teaching electrochemistry in the General Chemistry Laboratory through corrosion exercise. So, I'm going to talk about abstract. Electrochemistry is often considered one of the most challenging topics in general chemistry, as students tend to master quantitative calculation while struggling with conceptual understanding. This article presents an innovative laboratory approach that uses corrosion experiments to teach fundamental electrochemical principles, such as redox reactions, standard reduction potentials, galvanic cells, and chemical equilibrium, rather than focusing on batteries. The experiment introduces students to real-world corrosion phenomena under various environmental conditions, including neutral, acidic, and saline environments. Students measure voltage, current, and mass loss, and observe chemical change visually using indicators like phenolphthalein. They also investigate corrosion protection techniques such as sacrificial anodes and impressed current cathodic protection. The lab setup is cost effective, simple, and highly relevant to engineering and military application. Educational results showed improved student performance and engagement, particularly when the lab followed an introductory battery activity.
The objective of this experiment is teach fundamental principles of electrochemistry through the observation and analysis of corrosion instead of the traditional use batteries. Electrochemistry is a key topic in general chemistry courses, but is often one of the most difficult for students to fully grasp. While many students are able to perform calculations involving electrochemical cells, they commonly struggle to understand the qualitative aspect, such as identifying hard reactions, understanding the structure of gamma cells, and relating concentration and equilibrium to cell voltage. Traditionally, electrochemistry is taught using batteries and standard voltage cells. However, this article offers an alternative and highly effective approach, using corrosion as the main context to teach electrochemical principles. Corrosion is not only an important real-world phenomenon, but also a powerful example of electrochemical process in action. In simple terms, corrosion is the formation of an electrochemical cell between a metal and environmental component such as oxygen or hydrogen ions. This process leads to the gradual degradation of the metal. Sometimes that has enormous implications in engineering, naval operations, and infrastructure. Despite its importance, corrosion is typically underrepresented in general chemistry textbooks when compared to batteries. This paper argues that corrosion can be a more engaging and realistic way to help students understand key electrochemical concepts such as standard reduction potentials, electrolytes, galvanic cells, Le Chatelier's principle, and Henry's law. The authors designed a hands-on laboratory experiment that allowed first-year undergraduate students to explore corrosion directly. Students observe electrochemical reactions in real time, measure voltage, current, and mass loss, and investigate different methods of corrosion protection, including sacrificial anodes and impressed current cathodic protection. The experiment is simple, inexpensive, and fits within a standard lab period. It uses everyday material, like a digital multimeter and common metal, to simulate environments similar to those encountered in real military or maritime settings, such as fresh and salt water. In this presentation, We will explain the scientific background behind corrosion, describe the laboratory experiments in detail, and highlight the educational outcome of the innovative teaching approach.
The goal of this methodology is to help students better understand electrochemical concepts not just through calculations, but through hands-on visual experience using corrosion as the central phenomenon. To achieve this, a low-cost collaboratory experiment was designed that can be completed in a single session of about 3 hours. Students work in Paris and use sample materials such as digital multimeters, nails, zinc strips, salt or acid solutions, and pH indicators like phenolphthalein. The methodology is divided into 4 experimental modules, each focusing on a specific aspect of corrosion. First, students explore uniform corrosion here. Copper and zinc metals are connected in a salted water and distilled water. Voltage and current are measured to demonstrate how the presence of the electrolytes accelerates corrosion. Zinc acts as the anode and oxidizes, while copper acts as the cathode. Phenolphthalein is used to detect the formation of hydroxide ions, indicating oxygen reduction. Second, the effect of oxygen concentration on corrosion is examined. Two identical zinc strips are placed in a saline solution and connected to a multimeter. Then, air is bubbled near one of them. This introduces a potential difference that creates a measurable current, demonstrating how oxygen levels influence local corrosion rates. This reinforces concepts like Le Chatelier and Henry's law. Third, the students investigate corrosion in acidic environments using 3-molar hydrochloric acid to speed up the process. Iron nails and zinc pies are immersed and their mass loss is compared both when they are electrically connected and when they are not. This shows the principle of sacrificial anodes as zinc corrodes preferentially to protect the iron. Fourth, the method of impressed current cathodic protection is introduced using a 9-volt battery. Students connect the battery terminals to the metals and observe the effects on corrosion. Depending on the current direction, one metal is protected while the other corrodes faster. Gas bubbles are also observed, produced by the reduction of water and the cathode. Throughout the experiment, students record data such as a mass loss, voltage and current readings, and visual observation of the metal surface and pH indicator colors change. This methodology allows them to relate theoretical concepts to real, observable, and measurable phenomena.
After completing the corrosion lab, a student demonstrated a deeper understanding of electrochemical concepts, and the results were measurable both academically and through student feedback. According to the article, students performed significantly better on this laboratory exercise when it was preceded by a more traditional battery focused lab. In 2016, students who first completed a battery lab scored an average of 74% of the corrosion lab assessment. In comparison, in 2015, students who did not have the prior experience scored only 65.9%. The difference was statistically significant. This suggests that correction experiments work best when they build on foundational electrochemical knowledge, helping students reinforce and apply what they already learned. In addition to the scores, the author also collects students' feedback about the lab. Interestingly, 19% of students select this Corrosion lab as their favorite, and 70% say they learning the most from it, compared to another lab activities. Students who enjoy the experiment describe it as a heavy emphasis on what you will see in the fluid. Oh, interesting. To set the different reactions within the solution. And cool, to actually see corrosion happening. These comments highlight the visual and practical nature of experiment, which is especially effective for learners who would benefit from hands-on and observable results. On the other hand, a few students report challenges. Some said that the topic was difficult to understand or that they had no learning enough about corrosion in classes beforehand. A few also mentioned that the lab failed results, indicating that time management is important when implementing this activity. Despite this challenge, the overall response was very positive. The lab was run over 3 academic years with continued refinements and improvements, including better instruction and opportunities for discussion. Students working in Paris, and the experiment lasted about 3 hours. A worksheet guided, then talked about the theoretical content and the hands-on text, encouraging collaboration and critical thinking throughout the process. The skin of learning experience, where chemistry comes to life through visual reactions, real-world relevance, and the direct measurement makes a strong case for integrating corrosion into the electrochemistry curriculum.
Uh, Conclusion. To conclude this presentation, we can say that teaching electrochemistry through corrosion is not only effective, it's also engaging, practical, and highly relevant to the real world. The article demonstrates that corrosion is a powerful tool to help students understand core electrochemical concepts such as oxidation and reduction reactions, galvanic cells, and standard potentials, the role of electrolytes and environmental factors. Equilibrium principles include Le Chatelier's principle on and Henry Law. What makes this laboratory truly successful is its hands-on nature. Students don't just calculate voltage, they see the reactions happening. They measure current and they observe the bubbles and colors change, and they connect theory to observation. They also explore multiple strategies for corrosion prevention, from passive methods like sacrificial anodes to active control through the impressed current cathodic protection. The results show that the students learn more, enjoy the lab more, and remember the concepts better, especially when the labs follow a foundational activity focused on batteries.